Welcome to e-Pathashala for PG courses. So, we are looking at a series of talks on computer networks. So, we have been looking at a top down approach. So, we have looked at the application layer and some of the prominent protocols which are used at the application layer. So, next we will take a look at the transport layer. So, we will start with an overview of the transport layer and some of the protocols which are used at the transport layer. So, what we will do is we will first take a look at the transport layer functions and look at two common protocols which are used at the transport layer, namely the UDP protocol and the TCP protocol. We will also look at the details of the UDP protocol in this particular video. So, if you look at the layers, so just a quick recap of all the layers, you can see that we start with the application layer, then you have the transport and then the network and then the data link and the physical layers. So, if you look at this, the data link and the physical layer are link layer, they work at a link level, network works across the network, and a transport you can see is an end to end kind of a protocol. So, information that is added by the transport layer at one end is only interpreted at the other end's transport layer. So, it is an end to end protocol. Okay. So, application layer protocols also that we looked at were end to end protocols. So, transport layer similarly is an end to end protocol. So, we need to understand what this transport layer needs to do. So, as I said, the transport layer protocol are implemented only at the host. So, at the routers we do not have a transport layer implemented, okay. And the primary job of the transport layer is to provide some service to the application layer protocols, and of course, they will use the services of the network layer, okay, and rely on the network layer services and enhance its services. Okay. So, the primary function of a transport layer is process to process delivery, that is you could have multiple application processes which need to access the network. So, the transport layer sits in between the application layer and the network layer and provides a process to process delivery, that is process at one end to process at the other end. Okay. So, this function of doing a process to process delivery or taking the input from a process and passing it on to the network, and then from the network and passing it on to the correct process at the other end is referred to as multiplexing and demultiplexing. So, you have multiplexing happening at the sender end and demultiplexing happening at the receiver end. So, we also say that it provides a logical communication between the application processes which are running on different hosts. So, if you look at this picture, you can see that there are multiple devices which are there which form the network, and you have one machine at this end and another one which is at another end across across the network on a different network altogether. And this transport layer and this transport layer here talk to each other using a transport layer protocol, that is it provides a logical end to end transport mechanism. Okay, this is what we mean by an end to end transport mechanism, that is in between in the network nowhere is the transport information or the transport layer looked at. Okay. The transport there is no transport layer which is running at the routers, that is basically what we are referring to over here. So, as I said, this mux demux operation, you can see that there are multiple processes on this side and similarly multiple processes on the other side. So, this is the job of the multiplexer here, that is this is what the transport layer is doing, taking from the corresponding from the process and passing it on to IP to be delivered across the network and to be demultiplexed on the other end and passed on to the correct process at the receiving end. Now, as I said, to highlight the data link layer, network layer and transport layer passing of data, you can see the data link layer is a node to node passing of information. So, this is what happens here. So, when data is passed from an end node to the router, okay, across this link you have a node to node communication. Again from this router to another router is a node to node communication, it is a data link layer, okay, and then again from this router to this router it is again a node to node communication, a node to node communication here, a node to node communication here. From this host to this host you have a host to host communication, and at this host from this process to this particular process here, that is your process to process communication which is handled by our transport layer protocol. Okay. So, what are the challenges in handling this kind of an end to end protocol? Okay. The major challenge that we have as far as the TCP IP network is concerned is that this transport layer is running on top of the IP protocol, top of the network. Now, this then the IP protocol which is running at the network layer provides us only a best effort service. Now, what do we mean by best effort service? It does its best in order to deliver the packets, but it does not give us any guarantees, which means it could drop messages, it could reorder messages, it can also deliver duplicate copies of a given message, and it would limit messages to some finite size, and it could deliver messages after an arbitrarily long delay. So, there are delays, there is a reordering of packets, and there are packet losses. So, in spite of all these, we want to provide a good end-to-end service, even though the network is unreliable, okay, so to say, we want to provide some kind of a end-to-end service. This is what we are trying to do. Now, in addition to that, other desired characteristics are that we should be able to support multiple application processes on each host, and guarantee message delivery if possible, and deliver messages in the same order that they are sent, and deliver at most one copy of each message, right. So, this is what we would like to, that is, in spite of the problems that we have at the network layer, if we are able to provide all these characteristics, it will be a very ideal end-to-end protocol that you have. Okay. Okay. Also, we would like to support arbitrarily large messages. We said that the IP layer or the network layer may restrict you to the size of the messages. So, here we would like to have arbitrarily large messages if possible, support synchronization if possible, allow the receiver to flow control the sender, right. All these are things that are desired. Now, based on these desired characteristics, there are actually two different flavors of transport protocols that are used in the internet today. One is a reliable in-order unicast delivery protocol, which is the TCP protocol, so which also provides for congestion control, flow control, connection setup and so on. And the second is an unreliable best effort unordered unicast or multicast delivery protocol, which is the UDP protocol. So you can see that if you look at the major characteristics that we had or the desired characteristics of the transport layer, there is one protocol which tries to provide you all those desired characteristics to the best extent possible, and there is another which just does a basic end-to-end service, that is, provides just the basic service that is required for an end-to-end operation to take place, for a process-to-process communication to take place. So, UDP is that lightweight protocol, and TCP is a heavyweight protocol which tries to do a lot more in terms of providing you a reliable service. So, we say TCP provides reliable service, UDP provides unreliable service, but both are transport layer protocols and both provide the basic transport functionality which we expect. Now, remember that the basic transport functionality that is expected is the multiplexing and demultiplexing operation that we have. So, if you do a quick comparison of the UDP and the TCP protocol, we will look at details of these later, but just a quick comparison of their characteristics. The UDP protocol is a datagram oriented protocol, that is, it sends each message, each packet consists of a message. The TCP protocol on the other hand is a stream oriented protocol, that is, it looks at the data being sent as a stream of bytes, it is a byte stream protocol. UDP is an unreliable protocol, it is a connectionless protocol. TCP on the other hand provides reliability and it is connection oriented. UDP is very simple, TCP is complex. UDP supports both unicast and multicast, TCP is used only for unicast. And this is useful for a few applications, specifically multimedia kind of applications, whereas TCP is used for most internet applications which require a reliable delivery. For instance, your web, email, file transfer, telnet and so on, right, HTTP protocols, SMTP, all these run on top of the TCP protocol. It is also used for certain set of services like SNMP, network management, routing, naming and so on, where the reliability is not as important as the quickness of delivery, where you need it, since it is a simple protocol, it also happens to be fast. So, in those cases we make use of the UDP protocol. Now that we have had a quick look at the two protocols, we will take a look at details of the UDP protocol. Now, UDP, as I said, provides unreliable transmission of datagrams, and it is unreliable. Okay. And what it does is, it just merely extends the host to host delivery service of the IP datagram to an application to application service. That is, IP already provides you a host to host. On top of that, all that UDP does is identifies the application and sends it to the correct application. That is, all it does is just the basic multiplexing and demultiplexing operation. So, it adds just the information that is required for these two purposes, that is, for multiplexing on one end and demultiplexing at the other end. Okay. So, this is, you have different applications running on top of UDP, right. So, this is what you have, and this multiplexing and demultiplexing is done with the help of port numbers. So, in fact, UDP and TCP both use port numbers to identify the applications. So, a globally unique address at the transport layer for both UDP and TCP is normally considered to be a tuple, that is, the IP address comma port number, that is, the combination of the IP address and port number. So, based on this, an end-to-end connection that you would have, okay, both in UDP and TCP, is identified by means of these 4 parameters or 4 parameter tuple, that is source IP address, source port number, destination IP address and destination port number. So, these are 4 parameters which identify an end-to-end connection. So, source IP address, remember, will have the network address and the node address. So, you have identified the node on the network, source port number identifies the application on that particular node. Now, similarly, destination IP address will give you the destination's network and the node address, and the destination port number will give you the port the application on the destination side. So, your end-to-end connection is identified by means of these 4 parameters. So, this is something that we need to always remember very clearly. Okay. So, this is basically what will happen. So, when a packet comes in, you will have the UDP header having the port number, and inside that you will have the IP packet which is with the IP header. So, when you have when it comes to a machine, you basically check whether the machine address IP address matches. Once it matches, it is given to the transport layer. The transport layer will look at this port number to select the process. So, this is basically what happens in terms of the demultiplexing process. So, if you look at the UDP header, you find that it is a very simple header, right. It just has 4 bytes and 4 word, 2 words of 32 bits each. Okay. So, you have the header which is of 8 bytes. So, you have a source port number which is of 16 bits and destination port number of 16 bits. So, we said these two are 2 pieces of information which are required for doing the multiplexing and demultiplexing operation. Then there is a total length field of 16 bits and then a checksum field of 16 bits. So, this is all we have for the UDP header. So, when an application is using UDP and it passes it to the UDP protocol, all that UDP protocol will do is add this header to the data and send it off to the IP layer. Okay. So, as we saw that the port numbers are 16 bits, therefore, the port numbers range can go from 0 to 2 to the power of 16 minus 1. So, the maximum port number that you could have will be 65,535. The total message length can be at least 8 bytes, which means that the data field can be empty. Okay. So, that is what we are talking about over here. The message length is at least 8 bytes. So, which means I could have just a UDP header sent with no data at all. So, that is also a valid UDP packet. And at most it could be 65,535, as you can see that the total length is 16 bits. Total length of the packet is 16 bits. So, the total UDP packet size can be 64K. Okay. The checksum that we have is calculated for the packet of UDP and also some of the IP header fields, which is called as the pseudo header. The pseudo header consists of the source IP address and destination IP address plus the IP protocol fields. Now, the source IP address and destination IP address in the IP header, and this is part of the IP header, are used to identify that the end-to-end connection is intact. That is, we said that there are 4 parameters which actually identify an end-to-end connection: the source IP address, source port number, destination IP address and destination port number. So, we have the port numbers in the UDP header, but we do not have the IP addresses. So, these IP addresses are taken from the IP header, and this combination of source IP address, destination IP address plus the IP protocol field. Now, the IP protocol field will identify that it is the UDP protocol that is being used. So, source IP address, destination IP address and the protocol field. These 3 will identify that you are coming from the correct IP address and going to the correct destination address, and it will also identify that you are using the UDP protocol for the transport. Now, with this information, when you combine it with the UDP's header fields, that is the source port number, destination port number and total length, the checksum will be calculated on all these fields put together. So, with all these information being guaranteed by the checksum, you make sure that your endpoints are intact. That is, the delivery is taking place from this correct source IP address, source port number to the correct destination IP address and destination port number. The checksum that we use, let us take a quick look at what is actually happening over here. The reason we use checksum basically is to detect some errors that could be in the transmitted segment. Now, the way this checksum is calculated is a very simple process. The entire segment is basically treated as a sequence of 16-bit integers, and the checksum process just involves a simple addition. In fact, it is a ones complement sum of the segment contents. That is, you take the entire data, organize it as 16-bit integers, add them all up using ones complement addition, and that ones complement sum, right, that value is what is the checksum value, which is written in the UDP's checksum field. So, this is what happens at the sender. At the sender, you will add up all these things and put it in the UDP field. At the receiver side, what we need to do is, again you do the same process, that is you compute the checksum of the received segment, check if the computed checksum equals the checksum field value. Okay. If it is no, that is if it does not match, then that means there is an error. So, you will drop the packet. If there is an error, I am sorry, if there is no error, that is if the values match, then there is no error that is detected, but there could still be errors. I will leave it to you as a homework to think about why that could happen. Okay. But predominantly if your checksum matches, we assume that there are no errors and therefore, that the packet has been delivered correctly. So, this is what happens with respect to the checksum. So, in terms of the basic characteristics of UDP as such, you can see that it is a very simple protocol. It is a no frills, bare bones internet transport protocol. Okay. Absolutely no additional stuff, that is just the multiplexing, demultiplexing that you expect at the transport layer. And it is unreliable because packets could be lost and they could be delivered out of order to an application. Remember that this does not do any connection establishment or whatever. So, all that UDP will do is the moment it gets a packet from an application layer, it just wraps it up, adds this header, wraps it up and gives it to the IP layer. Now, IP layer will try to deliver the packet. If it does not deliver the packet or if there is no end machine waiting to receive this packet, that packet will be lost and UDP will be not even be aware of it. Okay. So, loss of packets is something that can happen. Similarly, packets can also be delivered out of order to the application. Now, UDP is not worried about that either. Okay. And there is no handshaking between the UDP sender and the receiver. Okay. So, so you do not know whether the receiver is available on the other side or not. Okay. So, then that is also not established, it is not UDP's responsibility to find that out. So, UDP does not bother about that. And each UDP segment is handled independently of others. Okay. So, each segment is a separate segment by itself. So, there are no sequence numbers maintained or whatever. Okay. All this, if you want, has to be handled only by the application. Okay. Now, given that you have all these minuses for a UDP protocol, why exactly would this protocol exist at all? Why should I have a protocol called UDP? Right. So, the reason for this is that in spite of its disadvantages that it does not provide all these services, it has a major advantage, which is that it is a very quick protocol. Okay. It is a lightweight protocol. Being a lightweight protocol, it acts very fast. Okay. And that advantage sometimes is useful for certain types of applications. Okay. So, why is it that it is very quick? So, understand that there is no connection establishment. Okay. Since there is no connection establishment initially, okay, there is no delay which a connection establishment process would cause. Okay. So, that delay is cut. Secondly, as I said, it is a very simple protocol. So, you do not have to maintain any connection state at the sender or the receiver. The sender gives the packet, right, the application gives the packet, sender side UDP just wraps it up, sends it to IP. The other side, it receives a packet from IP, looks up the port number and gives it to the application. If there is no process waiting at that particular port number, it will just drop the packet. So, no state maintained at all. So, it can be a very, very simple protocol. And the segment header, as we saw, is very small, just about 8 bytes, right, just 8 byte header. So, the overhead that you are adding for these for UDP is also very less. And it does not do any flow control or congestion control. So, it can just blast away as fast as desired. So, as long as the application keeps giving packets to UDP, UDP can just go on sending those packets at the right speed. So, it can just blast away at whatever speed. So, that is another advantage of the UDP protocol. Okay. And this kind of a feature that it can blast away at whatever speed is often useful for certain kinds of applications. We have already seen this earlier in when we talked about application layer protocols. We talked about loss tolerant and rate sensitive applications, typically multimedia type of applications, just streaming multimedia type of applications. Now, these applications can tolerate losses, okay, but they are very sensitive to delays, okay, and the rate at which the data is sent. So, for these applications, UDP happens to be a very ideal transport protocol. Okay. As I said, there are other uses of UDP as well for DNS and SNMP. As I had pointed out earlier, you can just think about why DNS and SNMP use the UDP protocol. So, remember that in DNS, which we have already looked at, DNS you can see that the client will have to contact the server and sometimes the server will contact another server and so on, right. You have the different ways, the iterative and recursive ways in which the protocol works. So, in those cases, it is a one time information exchange that you are looking for. So, it really does not make sense to establish a connection and then send the request and then get a response and so on. So, it makes sense to go in for UDP protocol which will just pack up the DNS request and send it off to the other side. But if you are looking for reliable service, of course DNS could also use the TCP protocol. Okay, so that is an option that is available. Okay, but typically other UDP uses are for DNS, and similarly for the network management protocol. Again in SNMP, for the network management protocol, when a network manager wants to talk to a device which is being managed, again it may just be sending may just be getting some pieces of information. So reliability is really not an issue over in these cases. So we make use of the UDP protocol, and it is a lightweight protocol. So we do not want to burden the network with a lot of data and with a lot of overhead. So wherever you want to keep it light, we make use of the UDP protocol. Okay. So which is why we see that UDP is predominantly used. Okay. Another reason that UDP is used is also that UDP can be used for supporting multicast. Now in TCP being a connection oriented protocol, it would be difficult to do a multicast using that. So, so whenever we want a multicast operation, it is easier to do it using the UDP protocol. Otherwise, if you are using TCP, it will be like doing multiple unicast services. So if you do not want to do that, and when you want to do a lightweight operation for multicast, then UDP becomes the ideal option. Okay. Now the question is, okay, if I need reliable transfer over UDP, then how do I do it? You will have to add all the reliability that you want will have to be added only at the application layer. Okay. And so in which case, if there is any error which has to be recovered, or whatever you need to do in terms of handling all these unreliability issues, all those will have to be handled only at the application layer. Okay. So everything, if it is handled at the application layer, that is what UDP would expect you to do. So if you are using UDP, you will have to handle other issues at the application layer. Otherwise, the other option that you have is that you will go for TCP. So if you want reliable data transfer, you will use TCP. So these are the two options that we have. Okay. So let us look at a quick example for how the checksum calculation is done. So as we said, the checksum calculation involves the header of UDP, the data of UDP, plus a pseudo header. The pseudo header is something which comes from the IP from the IP fields. That is, you use the 32-bit source address, 32-bit destination address, and the 8-bit protocol number which comes from the IP header. Now what we also do is the 16-bit UDP total length is also used again in order to form a full 32-bit packet for the checksum calculation. So you will find actually that the 16-bit UDP total length is there in two places, but that is how the checksum calculation is actually done in for UDP. So these are the additional pseudo header fields that I used. This is the header part of the UDP itself plus the data. So you will give take a few values and see how this whole thing will actually work out to be. So let us say this is the source IP address, this is the destination IP address. We have an all zeros field here, and this is our protocol number 17, which indicates it is a UDP protocol that is being used. Okay. So that is the information. This is the total length of the UDP packet. So if you look at the UDP packet now, so you can see that this is you have the port number specified. Okay, and this was our checksum field. Right. So this is our length field again, this is the checksum field. Now there is some data also that we are looking at. Assume that we have some data like TE, STI, NG as 7 bytes, and in order to make it again a multiple of 4 bytes, that is a 32 for it to end at a 32-bit boundary, we pad it with an all zeros over here. Okay, so there is 1 byte of padding that is used. So if you look at this whole packet that you have now, that is including the pseudo header, we basically organize this into 16-bit packets. So you can see this. So your 153.18 is one 16-bit part, followed by 8.105, that is followed by 171.2, followed by 14.10, then your 0 and 17, and then you have this 15, 0 and 15, then you have this 1087, which is again another 16-bit number, 13 another 16-bit number, 15 another 16-bit number, and then the all zeros. That is the place where the checksum would actually be calculated is assumed to be all zeros for the purpose of the calculation of the checksum. So you use a value of all zeros here, and then the TE, this forms the first 16 bits, then ST forms the next 16 bits, IN is the next, G and followed by 0. So what we do for the checksum calculation is that we add up all these numbers using ones complement arithmetic. So you just add them all up, and when there is a carry, you add the end around carry back to the number, and you will end up with a sum. So this is the sum that you get, and the checksum is the ones complement of this number that you have. So you have 100, 10, 110, 111, 01011 as a sum. So the complement of that becomes the checksum, and this is the value that will be stored in this checksum field. Okay. So when it is transmitted, and along with this checksum field, at the receiver end what would happen is the same calculation would be repeated, but the only thing is now instead of this all zeros field here at the checksum in the checksum field, you will have this checksum value actually sitting there, right. This value will be there. So, when you add them all up, what you will actually get is this sum plus this checksum also added. So, when you add up these two, what you will end up with is all ones. You can see that these two are basically the inverse of each other. So, when you add them up, you will get 1 plus 0, 1, 1 plus 0, 1 and so on. So, you will get a value of all ones, and if you take the ones complement of that, you will get a value of all zeros. So, this value of all zeros indicates that there is no checksum error. That is, we have added all these fields along with the checksum value, and you look for a total sum value of all zeros once you have taken the ones complement. So, that gives us a verification that the content including the data is intact. So, this is basically how the UDP checksum is calculated. So, to summarize, what we have looked at in this video is that we have looked at transport layer functions, the basic requirements. We have looked at how multiplexing and demultiplexing is done with the help of port numbers, and we have looked at these two flavors of the transport layer protocol, okay, the UDP protocol and the TCP protocol. We have also looked at the details of UDP protocol, which is a very simple protocol. It is a connectionless and an unreliable protocol. Okay. So, we will look at the details of TCP in the next session. Thank you.